For the lecture today, it's been made possible by a gift from Mr. John Chilton of the class of 1956. So we acknowledge that and thank him for that generous gift, which reminds me to tell you that all of you students and postdocs, once you graduate, remember to give back for these sorts of things. It helps a lot. And if you just designate it to the general fund, it'll go to be put in some commode somewhere. But you can designate it for things like this that could really be useful. So I encourage you to do that. Today we have Sir Konstantin Novoselov, and he was born in Russia, and he has both British and Russian citizenship. He's best known for isolation of graphene that he did at the University of Manchester in 2004. And he's an expert in condensed matter physics, mesoscopic physics, and nanotechnology. He was awarded the 2010 Nobel Prize in Physics for his achievements with graphene, along with Professor Guillaume. Kostya holds a position as the Langworthy Professor of Physics and the Royal Society Research Professor at the University of Manchester. He graduated from Moscow State University. He also got his PhD in the Netherlands and then moved to Manchester, where he worked with Professor Guillaume. And he's published over 200 papers, and he's won, of course, many other prizes, but once you've won the Nobel, you don't have to list all the others. And he was knighted in 2012, and so that's why officially he's got the title of Sir. With that, I turn it over to you.
Great.
Yeah.
Thanks, Logan. First of all, it's really great to be here. It wasn't planned originally. I was just in the area, wanted to drop by to see what Jim's group is doing, but then it just spiraled itself and then got into the lecture. So it's more or less ad hoc. But it's really, I had a very nice, pleasant day learning what people are doing at Rice. It's also, I should say, it's a very interesting geometry of the lecture. 3 screens, two microphones. They said one for NSA, one for CIA. That's really, I really appreciate. Right, so I'll try to talk to you on graphene, but also a little bit beyond graphene, what we are doing now. And the first slide, however, is dedicated for Boris, because I promised that there will be a few formulas in this talk, but I want to concentrate them all on the first slide. So this is our newly constructed Graphene Institute in Manchester. So we just launched it a year ago, and the formulas are just all around the walls here. We just took the first few papers from us, from Columbia Group, from several other groups on graphene, and then put them all on the walls. So that's basically all the formulas which you're going to see in the talk. Well, since we're on the building side now, let me tell you a little story. So that's how the building looks now. That's how it looked about 3 years ago when we were doing archaeological survey for the site, and it was quite exciting. You dig a lot of 70, 90, 80, 20 terrace houses in Manchester from the beginning of Industrial Revolution, but also remains of fairly large building over here, which was identified as an Albert Club house. So the Albert Club house, we probably won't know much about it, but this gentleman was the member of the Albert Club. So Boris is laughing at anyone else. A German guy with a beard, Industrial Revolution, Manchester. Right, it's Engels. So he was the member of this Albert Club house. Every single building on the university site is supposed to be named after a famous Mancunian. So like physics is Schuster building, math is Alan Turing building, and so on. So my immediate idea was that we should name the Graphene Institute the Engels building. Now the construction was quite heavily observed by the government. So when I passed this idea through George Osborne. He just tapped me on the shoulder and said, Kostya, we give you money to do research, not to explore your communist past. So it didn't work out. So we were waiting for the next general election. It didn't work out either. So the building still doesn't have a name. But similarly, as the Communist Manifesto hasn't been written by Engels alone, we're not concentrating on graphene in this building, so we're actually working on many other materials as well, and that's basically what this talk is going to be about. Right, so we all know about graphene. There are a number of superlatives, the thinnest, the strongest, the most conductive, so on, the most thermally conductive. But of course, the most interesting part is that all those properties are concentrated in a very simple material. It's only carbon arranged in hexagonal pattern. Despite it's very simple, it's actually not the hexagonal pattern is not the simplest Bravais lattices. It has 2 atoms per unit cell. Like I painted them green and red here, even though we all know that carbon atoms are blue. And if you just create quantum mechanical superposition of electrons sitting on two sides, you have symmetric, antisymmetric bonds, and then you get this famous pi star bands, and then the crossing at a certain area of the at certain place or in the Brillouin zone, which give you the famous linear dispersion relation, the Dirac cones, the Dirac materials, which are very, very popular now. And that's really the essence of many, many exciting electronic and optical properties of graphene. So I'm not going to go much into details about the pseudo-spin story and so on. Let me just summarize why this linear dispersion relation is very important, just in a few very simple cartoons. So generally, you know that all the materials around us all the conductive materials around us can be divided into 2 parts, where electrons conduct electricity and where holes conduct electricity. So N-type silicon, P-type silicon, copper, aluminum. So that's, if you want even simpler analogy, that's it's a country with a single party system, like Russia or North Korea. And people represent electrons, and those electrons or those people are free to move within the country. The moment you create a border, you create a junction, you create a border control, and then you can control the flow of people or the flow of electrons. So in a nutshell, that's all you need to know about modern electronics. So you take one N-type material, one P-type material, you link them together. That's how your computers operate. Graphene is fundamentally different because it has the same wave function that describes both electrons and holes there, particles or antiparticles, if you want to use the notations of the Dirac equation. And the analogy of the country here would be United States. I should apologize, it's from the previous election. It's not from this election. Sorry about this. And basically your N-type and P-type domains is like states. And even though you can have Republican or Democratic state, you still can cross the border without any problem. And that's why electrons in graphene can conduct electricity so well. They can cross from one type of electron or from one type of particles to another without any scattering, and that's why the high mobility of graphene. And then you can create even more complex quasi-particles, massive chiral fermions, if you want. But I haven't got an example of a country for that one, so I'm not going to talk about the bilayer graphene. So as I said, the electrons conduct electricity really well in graphene. If you characterize it in terms of mobility, it's how fast or how far electron travel without being scattered. It's easily 250,000 at room temperature, much more than 1 million at low temperature. For comparison, the same number for silicon is about 1,000, maybe a couple of thousand for the best HEMT devices. it's 50, 70,000. So in that sense, we are doing really good. However, it's not very good for logic devices because although those electrons travel very fast, you can't really stop them. You can't localize them. And that's an issue that for a good transistor, you need both properties, travel fast, but being able to stop completely. And that's what we haven't got in graphene. Then optical properties of graphene are quite interesting. It's only one atom. Despite of that, it absorbs quite a large fraction of light. It's actually visible. You can see it. So that's a sample, just a hole in copper foil. That's graphene. There is nothing here. That's bilayer graphene, and you can see that there is quite a sizable optical absorption. In fact, it's 2.3%. What is interesting for a physicist that this 2.3% is not given by any material parameter. It's only combination of the fundamental constants, pi times alpha. Do it at home, 3.14 divided by 137. So it's you get 2.3%. If you ever forget pi, look through graphene, measure the absorption, divide by alpha. That's your pi. So and in that sense, of course, the absorption is huge, but 2.3% of absorption for electronic engineers, it's nothing. It's very little. So that's why they try to use it for transparent conductive coating, which you need for touch panels or LEDs or LCDs and so on. So here is an example of such a device. It's a liquid crystal display. One pixel shown here, and then you can pinch off the optical transmission. Of course, you benefit here from the fact that it's highly conductive, highly transparent, but also flexible, also chemically inert as well. So things look quite promising, and it tells us that possibly the applications are with this material are realistic. But before we go to the promises for the future applications, let me pull a few which have happened already. And so what graphene has done for us already up to now? Well, it created workplaces in which it is mostly relevant for my PhD student, I'm sure for Jim PhD students as well. So they created a number of spin-off companies around the world and doing quite well. Now, it was meant as a joke until a couple of years ago. I received my regular copy of the Glamour magazine, and on one of the pages you read 5 jobs our kids will be doing, and then right next to virtual architect, avatar stylist, active makeup developer, there is graphene engineer. So if said by Glamour, should be true, right? It also provides entertainment as well. I'm sure that I don't need to advertise this sitcom in this audience, and in one of the episodes, Sheldon was trying to resolve the question why electrons in graphene behave as massless quasi-relativistic particles. You all know this already because of the 2 atoms per unit cell, but he struggles for the whole episode long because some of the formulas they are wrong. So those are for bilayer graphene, not for monolayer graphene. And it also gives shelter if you fancy to move to another state to tell a hydrofluoride that there is a graphene lane there. You can just now, but of course there are already applications out there. So a few years ago they started with the graphene racket, maybe most probably more a gimmick rather than a real applications. These days we have graphene car build. It's a real factory, so they build proper cars. Goes at £250,000 per car, and its body made of graphene composites. So it just increases toughness and so on. So, but of course, that's all still minor applications. Ideally, what we want is for graphene not to replace the existing materials. We want it to create new applications, which were not possible without this material, which have all this unique combination of the unique properties. So here is one example of the things which I mean. Here is the adaptive contact lens. So what you do, you take a contact lens, you put graphene on top, you put another one the same on top, you fill the gap with liquid crystal, and basically you can, by applying voltage, you can switch the focal depths of this contact lens. So you don't need several pairs of glasses, you have one contact lens which you can switch from far side to short side. And you can't use any other materials because it should be flexible, because it's usually PDMS, so it would be conformal to your eye, and transparent and conductive, and no other materials can do this job. And that's the sort of applications which we are really looking forward. And another one of those is the use of graphene as a perfect membrane. If you think about it, so graphene is completely impermeable; nothing can go through. So the largest particle which go through is the proton, right? No atoms can penetrate. At the same time, we can functionalize it, and then if you do it smartly, you can allow certain atomic or molecular species to go through. If you're really smart, you can do it. You can do it selective, and that's really good for, well, some of the basic applications is filtration, desalination. But what really excites us about this is the applications in biology, because biology is the physics of membranes. So what you allow through, what you don't allow through, and that's really that opens up a lot of applications in the healthcare, in life science, like artificial tissues, artificial skin, and so on, membranes, barriers, drug delivery, and so on. So let me now just say a few words about the mass production of graphene, because of course for some time we've been only limited to the material produced by the Scotch tape method, which we still use a lot in my lab. Is the fastest, probably the most reliable one. But of course, for the real applications, you want large area graphene. So otherwise, you can't really pull any proper applications. And before we go to the mass production of graphene, again, let me give you a little story. It's a little bit of my hobby. It's the history of graphite, and tell you a story about the mass production of graphite. Because graphite, quite interestingly, it was discovered and first mined for a couple of 100 years, very, very close to Manchester in Lake District in Seathwaite Valley, Borrowdale, close to Keswick. And so the first mention of graphite is 1555, and when they imposed the taxation of this on this material. They still didn't know what to use it for, but they already know how much tax to charge. And so the mines are still there. You still can go inside. Absolutely beautiful, really nice, nice place. Upsail for 30 meters, and then really nice environment. And then, but already, how fast things spread. 1565, we see the first mentioning of graphite in the book of Konrad Gessner, published in Zurich in the year of his death. And that's, so 1555, 1565, that's really, really fast for the Europe at that time. Our colleagues in Zurich only start to work on graphene now, so it's just, 12 years after graphene. So at that time, they were much faster. Now, at that time, it was the only mine in the world which produced high-quality graphite, and the owners realized it very quick. They intentionally limited the production, inflated the prices. At a certain moment, the price for graphite was a pound sterling per pound weight, and pound sterling was a huge amount. It's basically weekly, maybe even monthly wages for the miners. So it was quite easy to slip accidentally a rock into your pocket, and then here you are, you've got your monthly wages in your pocket. So they had huge problems with illegal access to the mines and stealing of the graphite, and the illegal market of graphite flourished incredibly. They even have to push for a special legislation through the parliament, which punished illegal access to the mines, and the punishment was the hard labor for 1 year and public whipping. And I still remind all my students that if you touch graphene in the lab, you are condemned for 4 years of PhD, hard work for PhD, and then public whipping at your viva. And even the title for this slide, the black market, they say that it originated from the illegal market which existed for graphite in 17th, 18th century Britain. Well, these days there is fairly legal gray market of graphene, and one of the players, well, some time ago, was one of my students opened a company and started to sell mechanically exfoliated graphene at some ridiculous price, £1 per square micron. And it was okay in the beginning when our flakes were very small, but we could quite easily get into millimeter size very fast. And then if you extrapolate, you get at some ridiculous price. And that's why I always tell them that he should get into more scalable production of graphene. And luckily, there are a number of ways how to do it these days. Depending on the quality and the price you want to pay, you go either to liquid phase exfoliation or CVD or epitaxial or molecular assembly on the surface. So that problem is, I would say, is more or less resolved these days. So you can, depending on the application, you can pick up your method of production quite easily. So now let me switch gears and tell you the story beyond graphene. So what's beyond that? I showed you that we managed to pull out this nice new building. We spent 10 million on equipment for the clean rooms and so on. And my students they're all very active, just bright eyes, bushy tails, keep asking me, Kosti, we spent all those money on equipment. Can we afford to buy not only the lead pencil, can we buy some other pencils as well? Well, the answer is yes, we can. And if you exfoliate other pencils, what happens is that you create two-dimensional crystals of other materials as well. So those can be 1 atom thick, same as graphene, but they originate from semiconductors or from metals. Some of them are from superconductors. So now you basically cover the areas which graphene couldn't cover by itself. Like boron nitride is a very good insulator. Niobium diselenide is a superconductor. Complex oxides or semiconductor like molybdenum sulfide, tungsten selenide, and so on. So now we have a range of different two-dimensional crystals. What is even more interesting that very often the properties of the two-dimensional crystal would be very different than the property of the three-dimensional counterpart. So that's exciting quite by itself. And the introduction for this part of the talk is that if you think about this, there are only few materials which determine our world. Like our electronics, 99% silicon. The construction engineering, we always rely on the strength of steel. So we can't live without that. Aerospace engineering is aluminum, a little bit of titanium. We don't notice this, but we are limited by the performance of those few materials. If an electronic engineer wants to create a new device, he should first consult what silicon can do for me, what's the band gap of silicon oxide, and then create a device based on that. Ideally, what you want is to mix and match different materials together, what we call composite materials or heterostructures. Those examples do exist already, but there are still few and far between. Ideally, what you want is to figure out what kind of properties do you want, and then create a material by scratch on atom by atom, or at least layer by layer engineering, and then you can get into and then you can create whatever stack you want with whatever predetermined property you want. Then you can say, I want my top layer to be sensor, the next one would be harvest energy, the next one would be logic, interconnect, sensors, and so on. And because we have now those two-dimensional crystals, we can potentially do exactly that, because we can if you come to a lab, you have the library of those different materials, all 1 atom thick. You can start combining them together into a random order, into a stack which never existed before. And I should say that those stacks, even more complex stacks, we do create in the lab, and they do have very unique, very new properties and new functionalities. Like the first 6 layers here would give you a very good tunneling transistor. It's a new architecture. It's vertical architecture rather than planar architecture, which we use for CMOS technology. The next few is the solar cell, and so on. So just to show you how versatile is this technology, here is one example of the tunneling transistor. You basically measure vertical current between 2 graphene layers separated by a very thin 1, 2, 3 layers of other materials, which are insulator. And here we use material called vermiculites, basically clay. The reason why I chose clay, well, I thought it sounds nice, clay transistor, but also because you can get it from any convenience store, because it's the main component of the cat litter boxes filler. So you basically you can make a transistor out of this clay, and you only need to make sure that you use it before it goes into the cat litter boxes, not afterwards. Right? And the quality of those heterostructures can be extremely high. So here is an example of one of the devices. It doesn't matter what does it do. We killed it at the end anyway, and we carved a small piece in TEM and pulled it out and looked at it so we carved it in FIB, and we pulled it out to look at it in the TEM, and you see all the individual layers. That's graphene separated by boron nitride on boron nitride substrate, so the quality is extremely high. Here is another example. So again, we started with boron nitride, which is an insulator, and then you put 2 layers of graphene, then 2 layers of boron nitride, 2 layers of graphene, 2 layers of boron nitride, and then 2 more layers of graphene. And it wasn't done to impress you. It was actually a working device. We were measuring tunneling through the gap opened in this bilayer. But if you look especially in the dark field image, you won't say where the thick BN stops and where the heterostructure starts. So potentially the quality can be extremely high. But in comparison to the gross method, so here we can, with the van der Waals materials, because those materials are still not linked by any forces, a part of the van der Waals, you have a number of degrees of freedom. You can strain every next layer. You can rotate every next layer as well. And then depending on even on the relative rotation, your properties changes. If you try to be with me for 2 slides, then we would just pass quite safely through here. So it's probably the only physics slides which I've got here. So if you have 2 layers of graphene and you rotate them in the real space, you rotate them in the reciprocal space as well. So your dispersion bands do shift with respect to each other as well. And it's a very simple device. You just put 2 layers of graphene on top of each other, separated by some insulator. That's it. Just make sure that the disorientation angle is very small. And a very simple device, but the IV characteristics suddenly become very unusual. You increase the voltage, and the current first goes up and then goes down. So usually, it doesn't usually happen. If you have metal wire, you increase voltage, the current always goes up. So here it goes down. It goes down means it's negative resistance, and negative resistance means that you are pumping energy into the system. You don't emit energy like the ohms, the Joule heating, but you are pumping energy into the system, and that's very good for a number of applications like high frequency electronics, for example. So so it's called resonance tunneling diodes. The beauty of ours was that it works at low temperature as well as at room temperature. Usually the traditional ones stop working at room temperature. So everywhere you see the blue area is the negative resistance, so it's room temperature and low temperature, it's almost the same. I should say it was pointed by my collaborators at MIT that only Russian and British could call 200 Kelvin the room temperature, but believe me, it does operate at room temperature. So you just put it into LC circuit and you get self-sustained oscillations because it pumps energy into it from the power supply. But then so the explanation for that is that if you have two cones slightly separated in space, you can tunnel this electron only when at the places where they overlap in order to conserve energy and momentum. And unless you bias them properly, you can't tunnel. So that at this moment, your current start flowing. When the overlap is maximum, it's the maximum current. And then when you pass this point, the current goes down. The beauty of this effect is that you only need to know the elliptical cross section. So it's a purely geometrical effect. It's purely a geometrical effect, and what you studied in school, the cross sections of the cone, and here it means you see it in the shape of the IV characteristics. But the cones, the wave function of electrons is actually chiral. It has two components, and we see the chirality. So now it's not just elliptical cross sections; it's chiral elliptical cross sections, and we see it in our experiments as well. So I'm not going to further into the details, but so just believe me that you learn a lot from these very simple experiments. So then you can also ask, so what happens if you have this junction of two graphenes with some semiconductor in between? What happens if you bias them and then inject electron and holes? Can you emit light? Well, potentially yes, but you need to play a few tricks here because the problem is the time scale would need to match, because usually those electrons and holes would like to escape very fast, and so you need to think a little bit to make proper band engineering. You put some buffer layers there and so on. But if you do that, this heterostructure can emit light as well. And here is an example of one of our maybe most elaborative heterostructures. Graphene is only here; it's only minor role. The light emission are those blue layers is the semiconductor with the direct band gap in it, and then if you apply voltage, you see light being emitted from this junction. So really, and yet it is still 10, 20 layers, so it's still very thin. So it's 20 atom thick, very flexible. If you want to make it transparent, you can make it transparent as well, and you can bring any functionality you want, from the transistor to solar cell to the light-emitting diodes. Because we have a large number of those materials, now we probably tried a few dozens of those materials. You can create light emitters at different parts of the spectra, or you can even mix them into one, and so on. And some of those materials really show very unusual behavior. Like usually your LEDs, the problems with the modern LEDs, the more brighter you make them, the less efficient they are. We have actually materials which increase the luminescence at higher temperature and at higher biases. So, and the reason for that is really in the band structure with the spin orbit coupling and so on. So I'm not going into details of that, but believe me, it's a very interesting area where the physics, which we just only now start to understand, it actually gets immediately projected on the properties of the applications which we can gain with those materials. Right. So I showed you a few slides about the mass production and the different applications. Let me now talk a little bit about the current applications which we are gaining with the other materials as well. So here is, we have, one of the production methods is the liquid phase exfoliation. You take graphene, you split it into individual layers, and you can do it in suspension. What you get is basically graphene paint or graphene ink. You can do the same with other materials as well. So this one, slightly brownish, greenish, is tungsten disulfide. It's a semiconductor. That's boron nitride. It's an insulator. So you can basically produce many other inks as well. Conductive, semiconductive, insulating. I won't say superconductive, but there are a number of different properties which you can gain this way. And then you can put them into your inkjet printer. Rather than putting RGB colors, you put graphene, semiconductor, and insulator, and you can start printing with that inkjet, and you can start print functional devices. For example, if you put some semiconductor material in between two conductive materials, you can make it into a solar cell. It's maybe not very high efficiency solar cell, but it still works, and it's extremely simple. So you can take simply 3 buckets, you paint on the wall with those 3 buckets, and here you get your solar cell painted. So, and those are semiconductor materials; they are properly stable, so it does work very well. Well, we're probably, and because they're still few atoms, only few atoms thin, they're still bendable, and they can be made semi-transparent as well if you want. Now, the first applications of those printed electronics with graphene is already there. It's already commercial. So graphene ink production is commercialized by several companies. So we collaborate. We have our own spin-off, which we use for to print RFIDs for Internet of Things applications, and you can print those antennas in both frequency ranges. And what is really exciting for me that for HF antenna, you need an insulator to be placed here, and we start to use boron nitride inks for the insulator. So the other 2D materials start to be used in printed electronics as well as graphene. So now let me again tell you a little story about the printed electronics. So I should apologize for the quality of the images. It's I drew them on a plane, so just don't be too strict about this. So the story takes us back to the Second World War. Germany airstrikes Britain. Britain airstrikes Germany. It's the first time when the radar started to be used quite heavily in military, and of course, German radars, they quite easily see British aircraft, and that's why it was quite easy to kill one. So how to avoid it? You need to blind the radar. How to blind the radar? You take you throw small metal pieces away from your plane, and those metal pieces create a cloud which reflects the radio waves, and then you don't see the airplane anymore, and you just can't hit the aircraft. The typical, but you can't carry too much weight, so those window material, as they call the chuffs, they use aluminum as the window material. The problem is that it was still, the UK was still blockaded by the U-boats. Alan Turing still hasn't cracked the Enigma code, so there was a huge shortage of aluminum in the UK. So they needed something else to reflect the radar, and they decided to print graphite on paper and use it as chaff material. So that's the Second World War. So here is this story from Hubert Idle, who worked for Oud and Weiberg. This company doesn't exist in the UK anymore, but I think it still exists in the US, actually. So, and here are a few lines from his memoirs. So he was summoned to the War Office, and within 24 hours of the first report, by working right through the night, 15 samples of different dispersions have been produced. So that's the sort of, I always show it to my students, that's the sort of speed I want. So 24 hours, 15 samples, that's so the two most promising samples were selected for bulk trials, and within a few days, a cask of each got into the mills. And then here is the graphene story. The issue with those inks is always printability. So you can take graphene and you can coat it on something, it will be conductive, but it's not very printable. You need binder. If you put a lot of binder, it goes in between the planes and it doesn't conduct. So there is always a trade-off there. So here is what they said. Thin flakes that overlapped were the best, and the study of different methods of dispersion indicated clearly the process, the form, and so on. So that's exactly what we do now with creating graphene ink. So when I read it, I felt ashamed. It took us 2 years to develop a recipe for very good graphene inks, and those guys they've done it within 24 hours during the wartime. So within 2 weeks, the mills were in full production, and hundreds of tons of window material were produced. They even put a graph of the resistance against the thickness of the coating. Typically, chemists know units, so you can't reproduce it ever, but it's good enough. Anyway, so these days we can produce large areas of those printed materials. It does work. It does work well. It's a commercial product, and it's better than traditionally used copper of aluminum because of a number of reasons. So where is the science here? Well, you always hear about the Internet of Things, that you need things to be interconnected. RFID technology is one of the technologies which goes into it, because it allows you without batteries to interconnect things, but you only transmit the name, the number of this device. Ideally what you want is to transmit some useful information, like what's going on in the environment. You need to put some sensors there, and because we now have a number of those different materials which can be produced as inks, we can print not only antenna, but also we can print sensors, and then our RFIDs can transmit some useful information. You put it into a carton of milk, you put it into a fridge, the milk turns sour, it measures pH, it sends a signal to your fridge, the fridge orders a new carton of milk. So that's how it works. And because we can print many different sensors, we can combine it in one, and we even print one universal sensor into those. So that's basically. I'm not going to go into the details how it works. So it does. There are several ways, from the cheapest one to most elaborative, and it's also nice that you can put coating into the textile fibers, and then your clothes start to be a sensor, start to be part of the circuit. And here is how it works. So that's the antenna. It's not connected to the computer. It's just laying on top of the receiver. That's the chip. That's the textile, which is coated by the semiconductor inks. And then, so there are no batteries here. You don't need batteries. And then, as you start heating it up, you transmit the temperature information to your receiver, because it's very easy to heat up something with the heat gun, and then it's very easy to read. But in fact, we can make those sensors so sensitive that even at the touch of a finger is enough to increase temperature. So fractions of degrees could quite easily be measured on this. So. I think I will probably stop here. I had enough. I hope you got a flavor of what is going on in terms of the graphene and materials beyond graphene and heterostructures. And I would just would like to thank all my collaborators back in Manchester, plus Sheffield and Nottingham. And thanks a lot for your attention.
Okay, so we're going to take questions, but this is being recorded, so we have a microphone. So if you have a question, we'll get it to you. John will get you the microphone. Over here, Jeff.
So you had mentioned combining these 2D-like materials into composites of multi-layered materials to maybe create a multifunctional material. However, if you want to combine things like a solar cell, maybe like a light-emitting device, it seems like the performance of each of those components would be better achieved if you were to use pure materials.
Well, not necessarily. So with the with the solar cells, we showed that you don't need monolayers there. So for the solar cell, you would probably use 3-4 layers to absorb most of the light. So it's the quantum yield for our solar cells was about 30%, which is quite decent, and we never bothered to optimize it. And because you can put different materials together with different band gaps, you can do what they do with gallium arsenide quantum wells, just absorb different part of the spectra in different layers. It's just an example. I'm sure that there are. I mean, I'm not trying to replace silicon, or I'm not trying to replace LEDs based on gallium nitride. But what I'm saying is that sometimes you would benefit from putting things together into one thin stack when you can design it for very specific purposes. You know, the good example is maybe optoelectronics with silicon waveguides. So you need very specific band gap of the material, which we can gain through molybdenum telluride, for example, which would match to the silicon photonics quite well, and then you can make both receivers and the emitters from the same stack. So applications, it would be very stupid to try to replace the existing applications for many reasons. But what I would like to look into the future and get into the applications which are not there yet, and say that we can tune the properties of the material to match exactly what you want, to give you exactly what you want, and maybe give you multi-functions if you need it.
When you have these materials that are produced by CVD, building them up layer by layer, very often the processing temperatures are very different for the different layers. Is that the problem?
Right. It's a very good question. So it's not a problem for me because we, in my lab, so I don't know nothing about growth. So that's my safe haven. So I take the easy part of producing the prototypes of materials from exfoliated flakes, exfoliated materials. Now, of course, if this is to go to proper mass production, people have to figure out how to grow it on large scale. And we just had a very good discussion an hour ago, because some of the leaders of the growth technology in this field are in Rice University. So I would probably readdress. So where is the agenda? I would probably readdress it to them. And the phase diagram there looks very, very rich. So because when you start growing those materials, you can either grow alloys of them, or you can segregate phases, and the segregation might happen either in lateral dimension or in vertical dimension. So that part is still a mystery for me. I think it's a mystery for most people. But it does work, but we still don't understand how in detail. So I can't. The only thing I can tell you that yes, you can do it, even though the processing temperature is different. Actually, the fact that the processing temperature is different is probably a good thing. You grow the lower melting point material first, you grow the higher melting point material first, the lower melting point material second. But in how it works in details, I don't know.
When you're stacking different materials into a van der Waals heterostructure, graphene is usually act as a transparent electrode. Do you think graphene is an electrode like a metal electrode, or do you consider any interactions between like TMDs and graphenes, for example, carrier transfers?
Right. So we're now getting into the maybe third level of complexion or of complexity with those heterostructures. Originally, a few years ago, people would just quite happily putting those crystals together. You treat them as non-interacting. Okay, at best you align. You just work out the work function there, and that's it. And of course, there is a lot of charge transfer, and so that's your next level. So how the band bending is happening. It's a little bit of a problem. What do you call the band bending for one atom thick crystal, and then especially when you have many of them, how does it happen? But yes, it does exist. So, and you can measure it quite easily. So if you make a junction, and it's vertical, but with the lateral side as well, you can shine light there, and you can see the charge separation, which tells you that there is band bending happening in the junction. So that's the second level of complexity. The next one is, you ask yourself, do they interact not only electronically but also atomically on the atomic level as well? Is there any surface reconstruction going on? The answer is yes, but up to which extent and at which angles of rotation it happens, at which not. So we're just now learning all those things about the stacks. But to answer your question shortly, yes, there is a charge transfer in between all those layers.
This question is not related to your lecture that you just gave, but I just know that your specialty is superconductor materials. I have a question that do you have any idea if high energy protons around 70 megaelectron volt to 250 megaelectron volt, when they interact with the superconductor, can they produce any secondary electron? And if not, is there any condition that we can apply those materials and produce the secondary electron? I know it's not related to your lecture, but I just wanted to ask.
Okay. Right. So the question is whether was it high energy protons can reproduce a secondary electron in those
Because
materials?
I'm a material scientist, but I don't know about the energy level of
Right.
materials. Keep in mind these protons, they are that high energy that they cannot have any electron in a metal and semiconductor materials.
I'm sure that there will be secondary electrons produced by proton radiation, but the proton permeation through graphene and boron nitride has been studied in reasonable detail. So mainly for the fuel cells and as a proton membrane, and so protons is at certain energy can penetrate through graphene. Actually, they penetrate quite easily through graphene. There is a paper, theoretical paper by Francois Peters on the dependence on the permeation of protons through graphene membrane, how it depends on the energy. If you type Peters and proton membrane, so that then it will be there. Let me direct you to that paper and right.
And then, do you think that the amount of the secondary electrons which produced will be higher than metal materials or
I won't expect so, because of course there is some bending finite ended rigidity of those membranes. You would lose some energy on this recoil. I would, if anything, I would expect it to be lower, but that's I can only tell you from the first principle. Sorry.
Thank you very much for your talk. It was fascinating. I was curious, for your RFID antennas, how do they compare to copper antennas in terms of power consumption and range?
I mean, so we have to optimize the ink quite a lot, and currently the performance is basically the same. So you cannot match the copper and aluminum antenna in terms of conductivity, but you can get pretty much close to that. So they perform quite similar. So 11 meters range for UHF, so and few tens of centimeters for HF. So very much similar to performance to the metal antenna. So in that sense, it's a properly commercial product.
Okay, so what I'd like to do is Mr. Chilton around? Is here? No. Okay. So I'd like to present you with this gift from the generous donation of John Chilton.
Thank you. Thank you.
Okay.
Thanks.
All right. Thank you.